So before the break, I mentioned that when we read the sun path diagram, we always use the solar time. So what does it mean by solar time? Before the invention of clock, people may tell the time from a sundial. Okay, do you know what is a sundial? Okay, this something like this, and then you have the compass, and so the shadows on the sundial will tell you the time of the day. Okay, so the time told by the sundial is the solar time, and the solar time is different from our clock time, because our clock time has been regulated according to the time zone, right? In Hong Kong, okay, we are in the time zone of GMT plus 8, right? So not only for a particular location in Hong Kong, but also for a larger region and many cities in China, okay? We have a large area with different latitude, different longitude, but still using the same time zone. But the relative location on Earth are different. Then the relative location of the sun to the Earth will also be different, but we are using the same time zone. So the solar time will be different from the clock time. Okay, for the solar noon time, okay, for the solar noon always divide the daytime into two equal half. Okay, into two equal half. But the clock time of 12 o'clock may not divide the daytime into two half. Okay, just like it is the sunrise in 6 o'clock clock time, but the sun may not set at 6 o'clock p.m. Okay, because these are clock time. But if you are using the solar time, when the sun set at when the sun rises at 6 o'clock, then 6 o'clock in the morning, then the sun must set in 6 o'clock at night in the afternoon, because we are using the solar time, and the solar noon is dividing the daytime into two equal half. Okay, so this solar time is the time referring to the location, to the local location of the sun. Okay, and for the clock time, it is adjusted to the time zone of the location. Okay, so next, why do we need to care about daylighting? Why should we utilize daylight? We human have invented many sophisticated technology like the artificial lighting. So even without daylight, we can still use electrical lighting. Okay, like in my office, I have the lighting. I have the fluorescent lighting. At home, I have lighting. Everywhere, actually, everywhere we have lighting. Okay, but still, we should utilize daylight as far as possible, because first of all, it is free. Okay, you don't want to pay too much for the electricity fees, then utilize daylight. Switch off the lighting and utilize daylight. So it is a natural energy. It has good lighting quality, or I should say the best. Okay, the best lighting quality. It will not flicker. Okay, unlike the fluorescent tube, especially when it is approaching to the end of its lamp life, the light will flicker. Okay, even for the incandescent lamp, actually it is flickering, because for the electricity supply, it is a 50 hertz electricity supply. So it means that the lighting level will actually flicker, but the frequency is too fast that we didn't aware of that, but it's actually flicker, and it enter to our brain. Okay, so you are not aware of that, but it doesn't mean that you didn't receive that flickering light. It has a full spectrum. Okay, so from 380 nanometer all the way to 780 nanometer. We have a full output, okay? Not full output, but we have a full spectrum, okay? A continuous spectrum of light. And it has excellent color rendering. Color rendering means to represent or to reflect the color of an object. Okay, so an apple is red and orange is orange. So under daylight, we see the true color of the object. But sometimes, like at night, when you are driving on the road, the lighting could be very yellowish. Okay, could be very yellowish. Then everything will be a shade of yellow and dark yellow to light yellow color. Okay. So for those lighting, it has poor color rendering. We will talk about what does it mean by color rendering in the lecture next week. Okay, substantial quantity. Okay, as long as we have the sun, then we have daylight. And variety. We don't want boring design. We want variation. We want something which will change. Okay, so the variety, constantly changing, daily, annual variation adds interest to the interior. Okay, so the light, the direction of the light, the shadows, it will reveal the form of the architecture. Okay, so daylight or sunlight is a very important design element in architecture. High luminous efficacy. Okay, so this is the lumen per watt. It's like an efficiency. Okay, like efficiency, but not exactly the same, because for efficiency, it's the power output divided by the power input. But for efficacy, the power output with a unit lumen, which is not the same as the power input. So anyway, high luminous efficacy means the daylight is very efficient. For per unit watt of radiation, it will give out high power output of light. Okay, so this efficiency is like the lighting power divided by the radiation power. Okay. Hygienic benefits. So sunlight can kill bacteria. Okay, so if you utilize sunlight, utilize daylight, then it means that you can have a more hygienic interior. Okay, and when you incorporate daylight, then you need windows. And human has a natural desire to look outside. Okay, we want to know what's happening outside, what is the weather, it is raining or it is sunny, and someone is yelling. So I want to know what is happening outside. And the window also provide an environment, a view for our eyes to relax. Okay, so these are the advantages for having daylight. So daylight is changing, daily changing. And then we have seasonal changing, like the sunlight direction, the sunlight availability, the intensity, they are changing daily and annually. They are unpredictable. So maybe this is a disadvantage. We cannot control how strong is the sunlight. It is unpredictable. So what is the sunlight availability tomorrow at 4 o'clock? I cannot tell you. Okay, no one can tell you. So it is unpredictable. It depends on the weather. It cannot be easily controlled. Okay, so if you have an experience reading next to the window, you will find that the glare is very annoying, and you may draw the blind. Okay, then draw the blind, maybe too dark, and then so. It is very difficult to control the sunlight or daylight to where we want them to be. Okay, so it's difficult to control. And it has solar heat gain or solar heat loss when you have window. So the window is always the weak point in the facade. Okay, in the facade, you may have a very thick wall to insulate the interior from the exterior. But when you need daylight, when you have the sunlight, you need an opening in the facade, right? So the window opening will have solar heat gain or solar heat loss, or heat loss in the winter. Okay, the glare that I have mentioned, visual discomfort, and for the window, then it is the weak point. So you may have noise intrusion, you may have rain penetration, water condensation, and so on. Okay, but still, I think nowadays the sustainability is the hot topic. Okay, we want to save the energy because we are running out of fossil fuels, so we want to minimize our energy consumption. So at the same time, we are using more energy efficient lighting device like the LED, but we still need to utilize daylight as far as possible. Okay, so although there are these limitations, some disadvantages, but we should utilize daylight when we can. Okay, daylight factor. For the assessment of the skylight availability, we use a parameter called daylight factor. So in the earlier part of the lecture, we have learned how to read this sun path diagram. And the sun path diagram is for sunlight availability. Okay, and in the beginning of the lecture, we mentioned that daylight can be treated as sunlight and skylight, right? So the sun path diagram tells you the sunlight availability. Then how about the skylight? For the skylight availability, we use the parameter daylight factor. Okay, so daylight factor will estimate the amount of skylight that you get of an interior. Okay, of an interior. So this daylight factor is to assess the skylight availability of an interior space. Okay, daylight factor is to assess the skylight availability of an interior space. And we have a very important assumption. We assume the sky to be heavily overcast. We assume the sky to be heavily overcast. So remember, in the first few slides, we have learned that there are three types of sky: sunny or clear sky, partly cloudy sky, and overcast sky. So for the evaluation of daylight factor, we assume the sky to be heavily overcast. So everywhere in the sky hemisphere is covered by thick cloud. Okay, and the cloud is so thick that we cannot tell where is the sun. Okay, so in the heavily overcast sky, the brightness of the sky will be the same irrespective of the orientation. Okay, so the brightness for heavily overcast sky, the brightness of the sky will depend on the elevation or solar altitude angle, but in the depend on the orientation. Okay, for overcast sky, the brightness of the sky will depend on the elevation angle, okay, whether it is near the horizon or high in the sky, and they are independent on the orientation. So even it is now early in the morning, I know that the sun will be in the east, but the sky is covered by thick cloud, and the cloud is so thick that the sunlight is redirected everywhere in the sky hemisphere, so that the brightness in the east or the brightness of the sky in the west are just the same. No difference. Okay, so it is the overcast sky. Okay, so back to daylight factor. Daylight factor is a ratio. Okay, it's a ratio of illuminance. So illuminance is similar to lighting level. Okay, illuminance. Okay, is similar to lighting level. So when it is brighter, okay, then the lighting level or illuminance is higher. Okay, so daylight factor is a ratio of illuminance at a point on a given plane due to light received directly or indirectly from a CIE standard overcast sky. So this CIE standard overcast sky is what I have mentioned. Heavily overcast sky. Okay, CIE is an international organization about lighting engineering. Okay, so CIE standard overcast sky is a heavily cloudy sky. And the daylight factor is a ratio of the illuminance, EI, okay, interior illuminance on a given plane, usually horizontal plane. Okay, on a given plane due to light received directly or indirectly. So for this point, the skylight can enter to the room, okay, can enter to the room directly. At the same time, it can also enter to the room indirectly through reflection, right? So due to this overcast sky, the light can directly light up the interior or indirectly through reflection. Okay, so this EI is the interior illuminance on a given plane due to this overcast sky. And daylight factor is the ratio of EI to the illuminance on a horizontal plane due to an unobstructed hemisphere of the sky. EO. Okay, EO is the horizontal illuminance due to the whole sky hemisphere. So in summary, daylight factor is a ratio of the interior to exterior. Okay, interior to exterior illuminance. And for the exterior illuminance, they are under the unobstructed sky. Okay, no obstruction. So if I have a building, okay, opposite to this room, then we have the direct skylight and also the reflected skylight entering to the interior. And EO, okay, for the EO, the measurement we should measure on the top of this building, okay, because if we measure the lighting level at this point, then this opposite building will block part of the sky, right? So in order to measure EO, we should measure it on the top of the tallest building around the room. Okay, so for the daylight factor, it is a ratio of interior illuminance or lighting level over the exterior illuminance under an unobstructed sky. So it is a percentage. Okay, we can multiply by 100% to find out the percentage of the daylight factor. Okay, daylight factor is a percentage. So if you're interested in the daylight factor, you can do a measurement. Okay, you can do a measurement. You find two equipment to measure the lighting level, and you need to ask your friend to help. So one of you stay indoor to measure EI, and then your friend. You will ask your friend to go to the top of your building, or if your building is not the top building around your neighborhood, then you have to go to the tallest building in your neighborhood, go to the roof, and then measure the lighting level at the same time. And the sky should be heavily cloudy. Okay, find a day when it is very cloudy. We have a thick cloud so you cannot see your own shadows, and then ask your friend to help. Go to the top of the tallest building in your neighborhood and measure the interior illuminance, EI, and exterior illuminance, EO, at the same time. The ratio will be daylight factor. Okay, so this daylight factor actually is to measure how densely packed is your surrounding. If you have a very tall building or very close tall building near to your house, then the daylight factor will be smaller, right? And it also represents the effectiveness of the window to transmit the daylight into the interior. Okay, how efficient is the window system to capture the daylight into the interior? Okay, so for the daylight factor, the higher, the larger will be the skylight availability. Okay. For the calculations of daylight factor, the indoor illuminance. So I keep mentioning the word illuminance. I haven't taught you what is the meaning, what is the exact meaning, definition of illuminance yet. So for this lesson, just consider illuminance as lighting level. Okay, how bright, how strong, how much light, okay, the lighting level. For the interior lighting level, it is composed of 3 components. So the sky component, which is the direct skylight entering to the interior. And we also have the internally reflected component. So the light entering to the room, reflected, and reflected again to the calculation point. So this is the internally reflected component. And we may also have externally reflected component. So the skylight hit the opposite obstruction and then received by the calculation point. So this is the externally reflected component. Okay, so the illuminance, the lighting level, will be the sum of direct skylight, internally reflected skylight, and externally reflected skylight. Okay. So I think for this subject, we will not go through deeply into how we can calculate the daylight factor. So I think you can find much a reference, many references about daylight factor, okay, in the internet or in the YouTube. Okay, you can even find it in the YouTube. So what should be the recommended values of daylight factor? Okay, so you ask your friend to do the measurement for you, and then you find out the daylight factor for your house. So you want to know, is it a good value? Then we refer to the British Standard or the CIBSE Code for Lighting. Okay, CIBSE is the Chartered Institution of Building Services Engineer. Okay, so anyway, some international code. And referring to these international code, for the bedroom, the daylight factor should be larger than 1. For the living room, should be larger than 1.5. For the kitchen, it should be larger than 2. So you will see that the kitchen has a higher daylight factor requirement. It's because of the hygienic environment. We want the kitchen to be free of bacteria, and we know that sunlight, skylight can kill bacteria. So it is recommended that the kitchen should have a higher daylight factor. Okay, so this equipment is called Illuminance Meter. Okay, Illuminance Meter. So this is a equipment to measure light level or illuminance. Okay, so we have these equipment in the laboratory. So later when we resume the face-to-face teaching, if you're interested, you can go to the lab and borrow the Illuminance Meter to have a try. Okay, in this picture, can you see the word over here? The word read ancient lights. Okay, ancient lights. So in some places, like in the UK, they have the ordinance regulating the rights to light. Okay, the rights to light claim state that if a window has been enjoying daylight for a long period of time, maybe 20 years, then if the opposite, okay, if the site opposite to this window construct a new building so that the new building obstruct the light that has been enjoyed by this window for a long, long time, then the owners of this window, the owner of this house can sue, can sue the developer of that new development. Okay, so in the window, it has a sign called ancient light. So it is to warn the people opposite that do not construct a tall building. Don't block my window, otherwise I will sue you. Okay, so you will see the right to enjoying daylight should be protected. Okay, and it has been it was even laid down in the ordinance for some country. Okay, types of daylighting system. So apart from windows, what kind of lighting system can we use to capture daylight? Okay, so daylight can be delivered into window through conventional windows, cholestery windows, or roof lights, as well as a number of remote distribution systems, such as light pipe. We will talk about light pipe in the later slides. Okay, so first of all, what is window? So we all know what is window, right? So windows have the advantage of providing both daylight and view out. And their disadvantage is that the amount of daylight delivered to the room will decrease dramatically as the distance of the window increase. So this blue curve, okay, this curve gives you the lighting level due to daylight. When it is close to the window, you have high lighting level, but the lighting level will drop dramatically when it is in the deeper part of the room. Okay, so that's why we need to have artificial lighting to supplement the daylight. Okay. Okay, cholestery window. So these are cholestery windows, and they are narrow strips of vertical or sloping window high up on the wall. It provides deeper penetration of daylight into the space below by way it will out. Okay, so usually these kind of windows will be very high on the in the high level of the room. So it is taller than people. Okay, so they are not for view out, and they are mostly for daylight. Okay, so it allowed deep penetration. Okay, because it is very tall, it is located on the top level, so it allows deeper penetration compared to the ordinary windows. Okay, for the ordinary window, it is lower, so it can only allow the daylight to penetrate in the zone near to the window. But when the window is on a high level, then it will be able to enter to the deeper part of the room. Okay, roof lights. Glazed opening in the roof of a building. daylight penetration from the roof light can vary widely depending on its design and the presence of internal devices to limit sun penetration. Okay, so these roof light in the Hong Kong International Airport, we have the roof light. And even in the Hong Hom train station, we also have the roof light. So roof light is just opening on the roof. And apart from the opening, they may also have some reflective device to reflect the light into the interior. So they are very effective to provide daylight over a large area. Okay, for a large area like this, storage factory, these are not artificial light. They are all skylight. Okay, so you see for a large area, and if there is only one story, then on the roof, we can open some holes to be skylight so that you don't need artificial lighting at all in the daytime. Okay, atria. They are often used to light a central circulation or social area by daylight emitted through a glass wall or wall. So this is the HSBC, okay, HSBC building, and they have a very large atrium. And the big window beside the atrium provide the daylight so that for the office worker near to the atrium, they can enjoy the daylight. Okay. So the main function of the atrium is to provide a pleasing visual experience and also a degree of contact with the outside. So if you're walking over here, it is in the middle or in the center of the building. But because it is next to the atrium, so it feels like you are somehow have a connection with the outside. Okay. And it also gives you a certain degree of daylight availability. Okay, the last slide is the light pipe. The light pipe is like water pipe. Okay, inside the water pipe is water, and inside the light pipe is light. So we use a circular pipe to transmit light into the interior of the room. So pipe collects daylight and sunlight on the external wall or roof and transmit it into the interior zone of the building by reflection. Okay, so in the light pipe, it reflect light to the interior. The efficiency of many remote distribution systems can vary dramatically from clear to overcast sky. Okay, so of course the light pipe will be most efficient when it can capture the sunlight, right? Because sunlight has a very strong intensity. So it will be more efficient to transmit sunlight compared to daylight. So this is also a light pipe opening, and it is a picture, it is a light pipe of the zero carbon building in Kowloon Bay. Okay, so if you have a chance, you can try to visit the zero carbon building. I don't know whether it is closed now. Maybe for this period of time it is closed. So later on, when we are back to the normal, then you can have a visit to the zero carbon building. So in the zero carbon building, there are many green features showcase. Oh, it is still open, right? Okay, good. So if you want to have a walk, okay, you can go to the website, the Zero Carbon Building, make a reservation, and then the personnel there will explain to you their sustainable system. They have the PV panel, they have the light pipe, they have many features. Okay, great. You have finished all the PowerPoints, and then let's take a short break. And then we have 2 tutorial exercise. I'm not sure whether we can finish all the tutorial exercise. Okay, let's try our best. I think the tutorial questions are not too difficult, and Okay, so let's start the tutorial. So during the break, we have explained once again how to read the sun path diagram. So I admit that the sun path diagram may be a little bit new to you, but actually it is just a coordination system, okay, a polar coordination system which include which tell us how the sun moves across the sky on different dates in the year. Okay, so let's take a look at the tutorial use of sun path diagram. Okay, you can enlarge the view if you need. So in this exercise, we are given the site layout plan of a residential estate in Hong Kong. Okay, just say imaginary layout plan. The windows of flat A and flat B face the same extent of external obstruction, but the window of flat A faces south while the flat B faces north. So this is the layout plan, and we may have a flat. Okay, this may be flat A, and then we have flat B. So flat A and flat B face the same extent of obstruction. Okay, same distance, same distance. The only difference between flat A and flat B is that flat A faces south and flat B faces north direction. Okay. The part of the sky blocked by the external obstruction has been plotted onto the sun path diagram. Discuss the following. Okay, so this is the difficult part. On the next page, we have the sun path diagram in Hong Kong, and I have briefly plot the external obstruction of flat A and flat B onto the sun path diagram. So first of all, let's take a look the sun path diagram, or the part of the sky visible to flat A, which is this diagram. Okay, this part of the diagram shows the part of the sky visible to flat A, and also the part of the sky blocked by obstruction. Okay, so you're right. You are yin long. Okay, the non-shaded area is the part visible. Okay, so here this part is visible and this part is obstructed. Okay, the shaded area is the part which is obstructed by the opposite buildings. How about this half of the circle? We have half of the circle also shaded. So this part of the sky would be part of the sky behind the window. Okay, for a vertical plane. Okay, for the vertical plane, it is only able to see half of the sky hemisphere, right? So when the window is facing south, then in the north part of the hemisphere, it will not be visible to the window. Okay, so this flat A, the window is, okay, for flat A, window is facing south. Okay, so the part of the sky behind south, okay, the part of the sky in the north direction, okay, this half of the sky will be non-visible to the window. Okay, so now the problem is, how can we draw these shaded area? Okay, how to draw this shaded area? So last night I have briefly drawn a diagram like this. Okay, so let's say this is flat A. Okay, let's say this is flat A, and opposite to flat A is a building. Okay, it is a building, and the part of the sky that is visible to flat A will be this portion, right? This portion of the sky is visible to flat A. For this part, it is behind the window. For this part of the sky, it is behind the window. And for this part of the sky, it is obstructed by opposite building. Okay, so only this blue color, okay, this blue color part is visible to flat A, right? So if we have the distance, if we have the distance D, and if we have the height H, okay, height H is the height of the top of the opposite building above the horizontal line of flat A. Okay, this is distance H. If we have H and D, then we can calculate the angle theta. Yes, tangent theta. So tangent theta will equal to H divided by D, right? So we can calculate this angle. And any part of the sky with angle smaller than theta will be not visible to flat A, right? Any part of the sky with an angle smaller than theta will not be visible to flat A. So this angle actually is the solar altitude angle. Okay, so for the part of the sky with altitude angle smaller than this theta, it will not be visible to flat A. So back to this sun path diagram, we may consider the angle theta sector by sector. Okay, for flat A, we may cut a section along this line. Then this line will be this line, right? We may cut the layout along this section and then find out a certain theta angle. Okay, find out a certain theta angle. So let's say the theta angle is equal to 30 degrees for that section. Okay, for this section, the angle theta is equal to 30. So this 30 degree is calculated from the opposite building. Okay, so any part of the sky lower than 30 degree will not be visible to flat A. So for this part, 30 degree over here, okay, 30. So we draw a line over here. So this is 30 degree. Okay, so for this small sector, any part of the sky with an angle smaller than theta will not be visible. So here, for a particular sector, you may divide the layout plan for every 10 degree or even 5 degree for each sector. So here, I divided by a sector of 10 degree. Okay, so from 5 degree to negative 5 degree, I estimate this theta angle to be 30. So for this sector, okay, this part of the sky with a theta angle less than 30 will be non-visible or invisible, okay, invisible to flat A. Okay, and then we may divide the layout in many more sector. Okay, so we may divide it for many more sector. Okay, I used 10 degree. Okay, I divide the external view of the flat for every 10 degree. So every 10 degree, I calculate the angle theta. Okay, like this angle. Okay, for this angle, maybe around 45 degree. Okay, around 45 degree, it will be somewhere here. Okay, so for this sector, I calculate the angle to be maybe around 25. Okay, here this angle is 25 degree, right? I trace the line, so 25. So any part of the sky behind this line, okay, or below the angle of 25 degree will be invisible to flat A. Okay, so by doing this exercise, I can plot all the lines on the sun path diagram. So this part of the sky will be blocked by this wall. Okay, this wall block this part of the sky. Okay, this part of the sky was blocked by that wall. And then I have this wall. Okay, these few walls will block this part of the sky. Okay, this part of the sky was blocked by those walls. And I also have okay, this part and this part of the walls, and they will block this part of the sky. Okay, they block this part of the sky. Where those walls? So let's look at for this example. Okay, this is the wall. This is also the wall. Okay, I draw a line up to this point. Okay, so it is just like I cut. Okay, I cut a section, and the section will be like this. Okay, this wall will be this wall. Okay, and flat A will be over here. Okay, this is flat A. So now I can calculate the angle theta. And any part of the sky with the angle smaller than theta will be invisible to flat A because it is blocked by this building. Okay, blocked by this wall. Okay, blocked by this wall. So this wall will block this part of the sky. Okay, so I calculate the angle theta and then plot onto the graph. So for that section, I roughly guess that this is the part of the sky blocked by this wall. Okay, and then I may cut another section. Okay, I may cut another section and then once again calculate the theta angle. Okay, I need to cut another section is because this D will be different, right? For these line, I have different D. Although the height these 6 buildings have the same height. So the H will be the same, but D will be different. Okay, so the theta angle will also be different, right? So for all these lines, like for this line, okay, this line, not perpendicular, but a little bit with a small angle, maybe 10 degree. Okay, for this part, I calculate another theta angle and then conclude that that part of the sky will block, that wall will block this part of the sky. Okay, so we repeat this exercise so all parts of the sky being blocked by the obstruction, by the buildings, can be plotted onto the sun path diagram. Okay? Is it okay? How many of you understand what I'm talking about? All right. Okay. Thank you. Thank you, Chi Long. So I think you have to have some imagination. Okay, you have to imagine if this is the sky dome, then what are the angles? How can we visualize? How can we visualize how the sun path move across the sky and how the building may block the sunlight? Okay, so the most important part is to calculate the altitude angles. Okay, to calculate this elevation angles. Okay, this elevation angle, and the part of the sky with a altitude angle smaller than this theta will be blocked by the sky. Okay, will be blocked by the sky. And we draw lines. So in this example, I divide the external view for every 10 degree. If you want to do it more accurately, then you can divide it into 5 degree. Okay, every 5 degree or so. So this is only a rough method. Okay, for you to plot the part of the sky being visible or invisible to the flats. Okay, so what I have done is for flat A, and we can examine when will flat A see the sun. Okay, so for flat A, can the occupants see the sun rise? No, because when the sun rises, the sun will be over here, and they are invisible. Okay, so the occupants in flat A will not be able to see the sun in the morning until around 11 o'clock in the winter. Then they will start to have sunlight. And until around 3 o'clock, the sunlight will be briefly blocked by 1 hour. And then after 4 o'clock, they have the sunlight again, and they will be able to see the sunset in the winter. Okay, and then in spring, they have sunlight after maybe 8:30, and then the sunlight will be blocked before 4 o'clock, and they cannot see the sunset. And how about summer? In the summer solstice, okay, 21st of June, the sun will be behind the window for the whole day. So for the occupants in flat A, they will not be able to see the sun in the summer solstice. Okay, not a single hour. They will not be able to see the sun. Okay, so this is the time that flat A will be able to see the sun. Okay, so if you are interested to the sunlight availability for your home, actually you can try to briefly plot the external obstruction onto the sun path diagram, okay, you have to know the orientation. So let's say for my home, maybe it is facing southeast. Okay, so for a window facing southeast, then this part, okay, this half circle of the sky will be blocked, okay, will be behind the window if a window is facing southeast, okay? And then you can try to plot the external obstruction to see when you have sunlight reaching your window. All right. So this is for flat A. Okay, the concept of stand at north towards south. What do you mean by stand at north towards south? Okay, maybe is it because do you mean the old saying by the Chinese that when 坐北向南, right? Okay, yeah. So actually, this is a example showing a window facing south, the difference of the sunlight availability for a window facing south and facing north. So for flat A, it is 坐北向南. So it is a windows facing south direction. So you will see that it has a high or large availability to the winter sunlight, right? So this is the winter sunlight. So you have quite a large amount of winter sunlight. And then this is autumn and then spring. And for the hot summer, the sun is actually behind your window. So you will be shaded from the hot summer sunlight. Okay, so this is the good point of flat A. How about flat B? Flat B. Okay, so this is the sun path diagram for flat B. I just use a mirror image. Okay, the mirror image for flat A will be that for flat B. Okay, so for flat B, the winter sunlight, these are the winter sunlight, and all of the winter sunlight is behind the window. Okay, so in the winter, it is cold and we want the sunlight. But if the window is facing north, no way you can enjoy the winter sunlight. And the sunlight availability is actually very little. Okay, in the morning, no sunlight. And then in the middle of the noon, you have the sunlight. And then 1 o'clock, 2 o'clock, 3 o'clock, 4 o'clock, and you can see the sunset in the summer. But usually in the summer, okay, in June, July, you don't like the sunlight. It is very hot. So you will probably use the curtain, use the blind to block the summer sunlight. Okay, so comparing the sunlight availability for flat A and flat B, we will know that if the window is facing south, like flat A, you have a large availability to the window, to the winter sunlight, and the summer sunlight will be behind you, okay, in the hottest days. And for the flat facing north, you don't have winter sunlight. And when you have sunlight, it will be in the hot summer. So you will probably want to block it. Okay, so that's the essence of this exercise, to examine the sunlight, the difference in the sunlight availability between two windows, north and south. Okay. I know that in your assignment, I don't know which assignment, but I know that you have to examine, you have to have a site visit to some buildings in Hong Kong and then try to plot the obstruction and the external shadings on the sun path diagram. Okay, so in this tutorial exercise, I have taught you how to roughly plot the external obstruction onto the sun path diagram. So in your assignment, maybe you can try, okay, to do something similar. And how about for external shading? External shading. So what is external shading? Let's take a look at a section. Okay, I am drawing a section. I have a window. Okay, this is a flat. Okay. I have a window over here, and the external shading could be an overhang. Okay, this is an overhang. In the top view, okay, in the top view, room. Okay, this is the room. And then I have a window, and the overhang may be like this. Okay, the overhang, the overhang. And how can we plot the part of the sky being blocked by the overhang? We may consider these 2 points. Okay, so for these 2 points, you can find out the azimuth angle as well as the altitude angle. Okay, you can try to find out the azimuth angle and the altitude angle, and then plot these angles onto the sun path diagram. To make it easier, maybe you can consider 4 points. Okay, for these 4 points, find out the azimuth angle and also the altitude angles. So for this point, the azimuth must be, okay, it will be a 90 degree. Okay, so let's say for these 4 points, considering maybe the center or maybe the windowsill, okay, the middle of the windowsill point, okay, you calculate the solar altitude, not the solar altitude, the altitude angle, okay, and the azimuth angle, and then plot them onto the sun path diagram. So for example, for the overhang, okay, let me draw an isometric diagram. Okay, this is the overhang, and then I have a window over here. Okay, so for the calculation point, maybe I take it over here. Okay, so this is the elevation angle. Okay, so let's say this angle is how much? Maybe 40. Okay, maybe 40 degree. And then for this point, okay, for this point, I measure the altitude angle, maybe 35 degree. Okay, maybe 35 degree. And I want to plot these 2 points onto the sun path diagram, okay, for flat A. So let's say, okay, 40 degree, where is 40? Okay, so 40 over here. Okay, so 40. So this point, 40, will be this point. Okay, and then 35. 35 will be somewhere here. And I also need to calculate the azimuth. Okay, this azimuth angle. So let's say this angle is 80. Okay, maybe 80. So 80, then draw a line. So this is for 80. So 80 and an altitude angle of 35. Then this point will be somewhere here. Okay, right? Okay, so we have this point and this point, and we join these two lines. We join these two lines, and similarly for the other side. Okay, for this point, it will be somewhere here, right? And then for this point, 40 degree, it will be somewhere here. Okay? And we join the line like this. And you may calculate one more angle for the midpoint of the overhang. So for the midpoint of the overhang, you calculate another altitude angle. So let's say the altitude angle is maybe 50. Okay, so if it is 50, then this point will be somewhere 50 is not reasonable, maybe 60. Okay, so if this angle is 60 degree, then it will be here. Okay, midpoint 60. Okay, so we draw a line like this. So this line will be the edge of the overhang on this side, and then this side, the red color, will be the overhang over here and the overhang over here. Then the part of the sky bounded by these lines will be the part of the sky blocked by the external shading. Okay? So this is how you can plot the overhang onto the sun path diagram. I know that it is quite complicated because you have just learned what is the solar altitude angle, what is azimuth, how does the sun moves across the sky, how to read the sun path diagram. And now you need to learn how to plot the object onto the sun path diagram. It could be quite complicated, but you can review the video. I'm doing the recording. So for your assignment, okay, you can try to draw what is the effect. You can examine, okay, what is the effect of an overhang to an interior, to the sunlight availability to an interior. Okay, so maybe you can think about this sun path diagram for this week. Okay, let it settle. Okay, give you some time to digest the material, and then you can watch over the videos and see if you understand how to draw the overhang, the shadings onto the sun path diagram. We can discuss about the sun path diagram again next week. Okay. Now one more tutorial that I want to share with you is the calculation of solar angles. Okay, so I admit that we have much to go through today. These calculations are straightforward, okay, not difficult, but okay, it's new. Okay, now you are learning many new things, and then for this tutorial exercise, there are new equations. So see these sine, cosine equations, and they are used to calculate the solar altitude and solar azimuth angle. So in the sun path diagram, how did someone plot the sun path onto the sun path diagram? First of all, they need to know where is the sun at a particular time on a particular day in a year, right? So according to time and date, we can use some equations to calculate the solar altitude angle and the solar azimuth angles. And the calculations are explained in this tutorial notes. Okay? So we have learned these two angles, solar altitude and the solar azimuth. I'm not going to explain again, so please read it. The sun position, and therefore these two angles changes with time. Okay, we know it. And the solar declination. What is the solar declination? The solar declination is the angle between the line connecting the sun and the earth and the and the plane containing the equator. Okay, which is the equatorial plane. So this equatorial plane will be this plane. Okay, this is the plane containing the equator. And oops, I erase it. Okay, let me draw it again. The equatorial plane is this circle. And the plane containing the Sun-Earth line, or the plane of the Earth orbit around the Sun, will be this one. Okay, this is the plane containing the orbit of the Earth around the Sun. So the angle between the Sun-Earth line. So let's say the Sun is over here. Okay, the Sun is over here. So the Sun-Earth line will be the line joining the Sun and the Earth. I think I made a mistake. I'm sorry. So here, this equatorial plane should mean the plane containing the orbit of the Earth around the Sun. So this equatorial plane should be this plane. Okay, the plane containing the Earth orbit around the Sun. Okay, and the Sun-Earth line will be the line joining the Sun and the Earth. So let's say it is now the winter solstice. Okay, 21st of December, the Sun is over here. Okay, the relative location of the Sun is over here. Then the angle between this line and the plane containing the orbit of the Earth will be this angle. It is called the solar declination. When it is on the north, it is a negative value. When it is in the south, it is a positive value. Okay? So when does I made a mistake again. I'm so sorry. So let me repeat once again. So the Sun is over here. This is the Sun. Okay. So in the beginning, I was right. Okay. In the beginning, I was right. So this equatorial plane is this plane. Okay. So this is the plane containing the equator. So the equatorial plane. So I just wonder why I was wrong. Okay. So the equatorial plane was the plane containing the equator. Okay. And the Sun-Earth line. This is the Sun. And then the line joining the Sun and the Earth is this one. Okay. The Sun-Earth line. sun path line. So your student Yin Long asked if it is the sun path line. Sun path. So for the sun path, it will be this one. Okay, this is the sun path. But this line is the line joining the sun and the earth. Okay. So the solar declination is the angle between the ecliptic one. The ecliptic one is the orbit, right? The orbit. So the orbit. So yeah. So this line is like the orbit, all right? But in this diagram, we are imagining the sun revolving around the earth. Yes, the orbit of the sun, but yeah, the relative orbit of the sun, right? We know that we are revolving around the sun, but you can also imagine it to be the sun revolving around the earth, right? So here, this is the orbit of the sun revolving around the earth. So they are the relative values. And the sun, when it is the winter solstice, the sun is over here. So the sun-earth line will be this line, okay? And the equatorial plane will be the plane containing the equator. So the solar declination, okay, the solar declination is the angle of the sun-earth line to the plane containing the equator. That is the orange plane, okay? The orange plane is the plane containing the equator. So the solar declination is the angle measured from the line joining the sun and the earth to the plane containing the equator. And it is negative value for the winter solstice. Okay, for the object in the south of the equator, the solar declination is negative. And for an object in the north of the equator, the solar declination is positive. Okay, so for the summer solstice, the solar declination is positive 23.45. So remember, in the solar solstice, the North Pole is pointing mostly towards the sun. Okay, and in the winter solstice, the North Pole is pointing mostly away from the sun. And the angle is equal to the tilting angle of the Earth axis, 23.5, or more accurately, 23.45 degree. Okay, and how about in the equinox? Okay, in the equinox, this is the line joining the sun and the earth. And this line is actually on the equatorial plane. So the solar declination will be 0. Okay, the line joining the earth and the sun is on the equatorial plane. Then the solar declination will be 0. Okay, the solar declination will be 0 degree. I know that it is very difficult to understand the measurement of these angles and the definition, but I want you to remember that on the winter solstice, okay, on the winter solstice, the solar declination is negative. Okay, negative 23.45 degree, which is the largest magnitude of the solar declination. Okay, so this angle is actually the tilting angle of the Earth north to south axis. Okay, this is 23.45 degree. Okay, so this is the largest value. And similarly, for the summer solstice, the solar declination is also the largest value, 23.45. But this time it is positive. Okay, in the winter it is negative. And in this spring equinox and the autumn equinox, the solar declination would be 0. 0. Okay, I want you to remember this. Okay. So actually, you may use this equation to calculate the solar declination angle. You will come up with these values. Okay, you will come up with these values. And you don't need to memorize this equation. Okay, in the test, it will be given. Okay, so you don't need to memorize. So what is N? N is the day number, counted from the first of the day until the last day in the year. Okay, so we assume there is no 29th of February. No. Okay, only 365 days in a year. Okay, so we may use this equation to calculate the solar declination. And then we have the hour angle. The hour angle is measured from the north-south vertical plane. Okay, so this plane is the north-south vertical plane. Okay, so the sun is moving across the sky like here. Okay, the sun is moving across the sky like here. So we may measure an angle. Okay, we may measure an angle between the sunlight and the vertical plane for the south and north direction. Okay, so this plane is this is the vertical plane for north and south. Okay, the vertical plane for north and south. So this hour angle is the angle between the sunlight, okay, between this sunlight and the vertical plane of north and south. So this is the hour angle. So at solar noon time, okay, at solar noon time, the sun will be along the north or south direction, right? So if you recall the sun path diagram, okay, this is the sun path diagram, and the solar noon time will be over here. Okay, the solar noon time will be over here. So that is the solar noon. The sun at solar noon will always moving, or will always be at the vertical plane containing the north and the south direction. And that's why the hour angle for the solar noon time will always be 0. Okay, hour angle will equal to 0 at solar noon time. Okay. And in the early morning, okay, the earlier the morning, the later in the afternoon, this hour angle will be larger. Okay. So for example, when it is 6 a.m. solar noon time, then the hour angle will equal to 15 degrees multiplied by 6 a.m. minus 12. So this is the hour angle, and it will be a negative values in the morning. And in the afternoon, the hour angle will be a positive value. Okay? Positive in the afternoon and negative in the morning. Okay, some more equations. Okay, the equation of time, this is an adjustment. Okay, so we know that we have 29th of February, and every day we have 24 hours, but it doesn't mean that the Earth revolve, or it doesn't mean that it takes exactly 24 hours for the Earth to make one rotation. Okay, but for our But for our time record, every day it has 24 hours. Okay, but the rotation, okay, for the Earth to make one rotation is not 24 hours. So we need some adjustment, and it is called the equation of time. Okay, so just some more equations, and I think we don't need to talk deep into the equation of time. And next is the standard time. So we mentioned that by using the sundial, okay, by using the sundial, okay, the shadows, we can tell the time, but this time is only solar time. Okay, so the solar time is this one. Okay, this is the solar time. T-S-O-L. Okay, this is the solar time, And the solar time is different from the clock time because for every location, it belongs to a particular time zone. Okay, for a particular time zone. So the time has been adjusted according to the time zone. So the clock time will not equal to the solar time. So here, standard time actually means the clock time of a location. Okay, the clock time of a location, we call that the standard time. Okay, so we have the solar time and the clock time. And this lambda standard is the reference meridian of the standard time zone. So for Hong Kong is negative 120 degree, and the local longitude is lambda LOC. And for Hong Kong, it is negative 114.2 degree. So this is just the geographical location for Hong Kong. Okay, and we add the equation of time that we learned how to calculate in the previous page. Then we can relay the solar time and the clock time. Okay, we can use this equation to relate the solar time and the clock time. And lastly, we have these three equations to calculate the solar altitude. Okay, what is solar altitude? The sun is over here, and the elevation angle. So this is the solar altitude. Okay. And next, we have two equations to calculate the solar azimuth. Okay, these two equations are used to calculate the solar azimuth. And the solar azimuth are measured from the south. So let's say this is south. Then the horizontal angle measured from the south is the solar azimuth. Okay. So in the solar altitude angle, we have LOC. LOC is the latitude. For Hong Kong, 22.3 degree. And then the solar declination, the hour angle. Because solar altitude depends on time, right? So it gives us the time of the day, and it gives the location. Okay, the location of the location where we consider we want to find the solar position. Okay, and the solar declination, this is the date. For solar declination, it gives us the day in a year. Okay, hour angle gives us the time on the day, and the local latitude will give us the location on Earth. Okay, so we use these to calculate the solar altitude. And for the solar azimuth, just similar. But there are two equations to calculate the solar azimuth. Okay, either two will be able to find the solar azimuth. Okay, and then in the later pages, these are some examples. I think we don't have enough time to go through all these examples, so I need you to read the examples yourself. And at the same time, I want to show you something more. So remember the sun path diagram. it depends on the location, right? So Hong Kong, we have this sun path diagram, and then for Beijing, that sun path diagram, London, that sun path diagram, in Sydney, another sun path diagram. So if you want to know the sun path diagram in another location on Earth, you can go to this website. I can post the website in the Blackboard after the lecture. So let's say for Hong Kong, the latitude is 22 something over here. And you can select different type of chart. So for the sun path diagram that we have learned is the stereographic sun path. So over here, I select stereographic sun path. And then the longitude is negative 114. Okay. So this is the sun path diagram for Hong Kong. And you can select a particular day in a year. Okay, like this is December, and then November, October, September, August, July, June, May, April, March. So today is the 5th of March. Okay, so this is the sun path of today. And the time is now 5:30. Okay, 5:30 in the afternoon. It will be over here. Okay, so the sun will be setting very soon. Let me check. Okay, the sky is getting dark. Okay, so sunset is coming. And you will see that the lines are very strange because these curves like a number 8. Okay, the curves like a number 8, these line shows the actual clock time, not the solar time. Okay, it shows the clock time. Can we switch it to solar time? Okay, not sure. Anyway, okay, so these are the time. Okay, so this is the sun path diagram for Hong Kong. How about in the Australia? Okay, in Australia, it is in the southern hemisphere. Then the sun path diagram will be like this. In the summer, okay, no, okay, I should say in June. Okay, in June, the sun path will be like this. So in June, they will have a short daylight hours. It is the winter. And in December, they have long daylight hours. Okay, from before around 5 o'clock, and then sunset at 7 o'clock. Okay, this is December. How about in the North Pole? In the North Pole, the latitude will be 90. Okay, so this is the sun path diagram for North Pole. In June, okay, in June, okay, this is the sun path, and then July, August, September. Okay, on this day, this is the equinox. So the sun will be rotating or will be moving across the horizon. No sunset. And then after the equinox, you cannot see the sun. Okay, in December, in November, you cannot see the sun because the sun is below the horizon. Okay, so this is a very interesting website that you can study the sun path of other location. And one more diagram I want to show you, which is for the calculations of the solar altitude and the solar azimuth. Okay. Let me share I want to show you the Excel. Okay, so this is the Excel file that I made last night. And on the column A, I have all the date from the 1st of January to February, March, April, all the way to December. And these are the day number, okay, from 1 to 365, and I use the calculations in the tutorial notes to calculate the solar declination. Okay, so in December 21st or 22nd, in the winter solstice, we have the smallest value of solar declination, the most negative values of the solar declination, negative 23.45 degree. And then in the summer solstice, we have the largest value, the most positive values. And on the two equinox, we have 0 degree. And on another page, this is the calculations for the solar azimuth, okay, solar altitude and the solar azimuth angles. And I want to remind you that in the equations, we use sine, cosine to calculate the angles. But there are more than one angles will give you the same sine theta value or cosine theta values. So for example, this is maybe negative 60. Okay, negative 60 degree give you sine theta of this value. But apart from negative 60, okay, about negative maybe negative 130. Okay, negative 120 will give you the same values for sine theta. Okay, because it is a cycle. So for sine theta, for cosine theta, it is a cycle. So if you just use the equations to do the calculations, you may come up with a wrong answer. Okay, so what I want to tell you is that when you use the equations in the tutorial notes to calculate the solar angles, okay, like these equations. Okay, when you use these equations to calculate the solar altitude and solar azimuth, you have to bear in mind how the sun path goes in the sun path diagram. Okay, you have to have an idea how the sun path will look like, and then you can double check whether the solar altitude and the solar azimuth angle make sense. I know that we overrun. We overrun is already 5:30. Okay. Any one of you have class at 5:30? Anyone? You can type in the chat box. So if any one of you have class at 5:30, you may now leave leave the virtual classroom and then attend your class. Okay, so I just want to explain some more about the calculations of the solar altitude and the solar azimuth. Okay, so when you do the calculations, like you calculate sine phi, let's say equal to what angles? Maybe let's say it's equal to 0.766. Okay, so sine phi equal to 0.766, and then you find out the sine theta, the theta value. Maybe the phi angle equal to 50. Okay, equal to 50 degree. But actually, you are trying to calculate the sun position on this day. Okay, and for the sun position on this day, what should be the azimuth angle? The azimuth angle should be larger than 90 degree, right? So this is the azimuth angle. So for this sun position, the azimuth angle should be larger than 90 degrees, should be 100 something. So the answer 50 doesn't make sense. It's because sine theta will equal to sine 180 degree minus theta angle. So this is the sine curve characteristics. So the answer will then should be 180 minus 50 equal to 130 degree. Okay, this should be the correct answer. Okay, 130 should be the correct answer. So when you do the calculations, you have to be careful. Okay, you have to be careful. So I think I overrun too much already. So I will no. I want to show you the once again the Excel. Okay, so for this Excel file in the tape solar angles, I have tried to input the equations for calculating the solar altitude. Let me zoom in. Okay, I have input the equations for calculating the solar altitude and the solar azimuth. And the two equations give different answer. And it doesn't make sense, right? Because they should come up with the same answer. And they have two different answers is because of the sine function and the cosine function characteristics. Okay, so here we are, I am calculating the solar, the sun position for 22nd of June. Okay, and for 22nd of June, the solar azimuth in the morning, okay, in the morning of 4 o'clock, okay, 5 o'clock, it should be a value larger, okay, it should be a negative values, smaller than 90 degree. It should be negative 100 something, okay? So this is 100 something, but not negative. It's because in the equation, we calculate from cosine phi, and cosine phi will equal to cosine negative 5. So the correct answer should be negative. It should be, we should add a negative to these values because they are in the morning. And in the morning, the sun is in the east, so it should be negative values. So negative these values. And from this equation, we are calculating from the sine function. And for the sine function, there are different characteristics so that it should be 180 plus these values and then negative so that we have the correct answer. Okay. So we have go through much, okay, we have go through much teaching materials. We have learned very much how to read the sun path diagram and then how to calculate the sun position, and you need time to digest. Okay, so I will stop here and I will add the I will post the website for examining the sun path diagram of other locations, and I will also attach, okay, I will also upload this Excel file to the Blackboard so that you can play with this Excel file, try to input other numbers, and then you can try to do the tutorial questions. Okay, in the tutorial, we have how many? We have 3 questions. Okay, the answers are already given, so you can try to read the solutions in the example. See if you understand the equations in the suggested solutions. Okay, so I have to stop here. I'm sorry that we didn't have enough time to go through everything. Okay, so I upload the Excel file and you should try to do the tutorial questions yourself. And I will also attach the website for the sun path diagram. Okay, so please try to play with the sun path diagram and to do the tutorial questions yourself. Okay, so I will stop here and we will meet again next week. Okay, next week in the virtual class.